Hello and good morning, everybody. Good afternoon, good evening, and thank you for joining. Hi, Priya. How's it going?
Hello, Alex. It's going good. It's going great. Thank you for asking.
Yeah, very good. So this is the first of our Road to Nodes workshop series. So I'm particularly excited and looking forward to this. So this is basically the kickoff to Nodes. So I'd like to do a few housekeeping words before we dive in. So this session is going to be recorded, so you can watch afterwards if you miss something or want to recap on anything. We will share a link to slides and to the code base that Priya will be using also in an email afterwards. So you can check that out there. I have a couple of lovely colleagues in chat who are helping out with questions. So if you have any questions during this session, please do use the Q&A panel or chat. Ideally use the Q&A specific one and type in your questions. There's David, there's Elaine, and there's Shiny. They will have a look. I will have a look as well to answer some of these questions. If by some reason, because lots of people have registered, we cannot answer your question directly, please don't be sad or mad. We will try to answer as many as possible. If you for some reason don't get an answer, take your question to our community page, community.neo4j.com. There is a huge platform, lots of people active there. So I'm pretty confident that somebody else will help you solve any questions or any problems you might have. Yeah, and one more thing, register for nodes. So if you are participating here today, that means you are obviously interested in nodes, but you are not automatically registered for nodes. So if you haven't registered for nodes yet, please go on our website. Please do so. I'll post a link in chat in a second. So you get the link there and you can register for it. But yeah, it's going to be fun. It's going to be two great days. Lots of conversations, obviously, but also great presentations. We are building the agenda and releasing it sometime later this week. So you should see the full glory of what's going to happen. It's going to be live across all the time zones. So that's a new thing. No matter where you are, something will be happening in your daytime. So you don't have to stay up late or go get up early, crazy early. There will be something happening in your time zone. So it's really good, and I think that's really unique event this time around. And yeah, it's going to be fun. So please register for it. Again, link is in chat now. Have a look. And I think that's it from my side. Anything else, Priya? I will chime in all the time if something happens, if some questions come up. But yeah, the stage is yours.
Thank you, Alex. Let me begin by sharing my screen.
And it's really great to see all these chat messages. So from all over the world, we have people from India, from Indonesia, from United Arab Emirates, from Northern Vancouver. What's VA? Virginia? VA? Sorry, I completely miss Northern VA. What is that? Some state in the United States. I should know this. Oh my God! Now I embarrass myself. Oslo, Norway, Algeria, Mexico, Colorado, Ohio, Costa Rica, Germany. So yeah, it's all over. It's really good. Really good to see.
Okay. Just give me a moment. I don't see my screen yet.
Yeah, no worries. Can I help you in some way?
No, that's okay. I'll just share my entire screen because I don't see the window somehow.
Okay. Maybe it was minimized. If it's minimized, you won't be able to share. You need to have it open.
No, that's okay. So do you see my screen?
Yes.
All right, so a very warm welcome to all of you joining in. As Alex mentioned, we are starting off with our training workshops today on the road to Notes 2022. And today's workshop is essentially an introduction. It's meant for beginners to the world of graph databases and Neo4j. So if you've heard about graph databases in the past, if you've heard of Neo4j in the past, and never really had a chance to explore what this is all about, well, then this session is for you. Well, this session.
Sorry, Priya, do you mind clicking on the little hide button
Yeah, sure.
Exactly.
Yeah.
Perfect.
Yeah.
Cool.
So we'd like the session to be interactive. Please tell us where you're from. Tell us how did you get to know about the workshop. And if you have questions, like Alex mentioned, please put them into the chat using the chat options available. And my colleagues are here from Neo4j to answer them for you. Right. So what are we covering today in the next 2 hours? Well, we've got a lot of ground to cover, but this is pretty much what we aim to. So we're going to start with graphs and why are they amazing? Well, that's the reason why we're here. So we'll start off with that. And then we're going to, help you with some guidelines for you to spot graph shape problems, right? So it's not enough having a graph database, but it's what you do with it that adds value to the whole proposition, right? So we're going to help you with guidelines to spot graph shape problems, and then put the graph database to use to solve for it. We will then turn our focus to Neo4j, which is essentially, again, why we're here. So Neo4j's, implementation of a graph is what we're going to look at in terms of the property graph model. And then we will also look at Cypher, which is essentially, Neo4j's graph query language that is used to load and also query the graph. We will have a hands-on during this workshop, and the hands-on will be on a sample movie graph that you will spin up yourselves. And it's going to be on our database as a service offering, which is called as AuraDB. And we're going to give you all instructions as to how you can spin that up and get that going. We will also have demos on the dev tool set that comes along with AuraDB. So I will be taking you through the entire tool set, so that you can familiarize yourselves with what's there so that, you can get started off with your journey with Neo4j. And then finally, we're going to look at the whole ecosystem at large. So of course, at the heart of the ecosystem is the graph database, which is Neo4j. But over the years, we've built a whole lot of tooling around the graph database that you can use to integrate your applications with Neo4j. Right? So we're going to look at what these options are that come along with the graph data platform, so that you can then pick and choose the best building blocks to interact with Neo4j. And finally, we're going to conclude with resources that you can use to advance your journey with graphs and Neo4j. So this will take a couple of minutes. So we'd like you to get started with launching your own AuraDB instance. Now, I'll take a few minutes to just talk about AuraDB. So AuraDB is our database as a service offering on the cloud. And it comes with a couple of options. So we have an option meant for professionals, who just want to get started. You can swipe a credit card and spin up instance of your own. No intervention from Neo4j required. And we also have an option for enterprise customers wanting to run their Neo4j workloads on the cloud. So this is pretty much a sales-led motion. So you'll have somebody from Neo4j sales contact you and then help the process going. But we also have a free version of AuraDB, which is meant for all you developers out there. So if you want to get quickly started with Neo4j, if you want to learn about Neo4j, if you have a hobby pet project that you want to do in Neo4j, well, then AuraDB free is the easiest way to get started. And it's, of course, free for forever and yours to own forever. So it's pretty much what you wish to do with it. So this is how you can get started with AuraDB free. You can go to dev.neo4j.com/aura-login, or you can go to console.neo4j.io. And please register if you're a first-time user, sign up, and you will be presented with two options there. One is AuraDB and the other is AuraDS. Now, AuraDS is our data science offering meant for all data scientists out there. But what you need to choose is AuraDB. And please make sure you choose the new instance and click on the movies graph that's available for you in the options that show up. Uh, that's all. That's all you need to do. And once you click on create, it'll take a couple of minutes to spin up. And what this will do is, it will load an instance for you with the movies graph preloaded in it, right? And we're going to have the hands-on on the movies graph, which is why we want you to pick the movies graph. Now, if you can't get to AuraDB, well, there's also an option where you can spin up a sandbox. So you can go to dev.neo4j.com/try. And you can also choose the movies sandbox that's available there. Okay, so I'm just going to keep the slide for a minute so that you can get this started. And, this will take a couple of minutes. So we'll come back to this once it's up and running. Okay. So just to show you how this would look something like this once it's up and running. I already have created my instance, before the session, and I already have my graph loaded. Once it's done, you will see 171 nodes and 253 relationships loaded in this graph. Now, don't worry about what this is. We will come back to this, but this is just to show you the interface and how it would look. All right, so I'm hoping everyone would do this, and I hope the links are in the chat so that people have access to this. Maybe just a few seconds, and then I'll switch over.
Yeah, absolutely. Links are in the chat. So if you're struggling with it, let us know. But you should be able to set up a or a free instance, or maybe you did your homework already and came prepared. So then you can post in chat and say you already done, and then we can continue.
Yeah, so I'm just going to flip through the slides. This is pretty much what you will see. When you create your first instance, pick the movies graph, and then it will take some time to set up. And then you can rename it if you so wish to, or you can just leave the default name there. Right. Okay, so we're going to continue then while the instance spins up. So we're going to talk about graphs, all right? And again, like I said, that's why we are all here. So back in the day, if somebody had to ask me what a graph was, I would have pointed to, what is the representation of it on my right, which is essentially a piece of graph paper. So it's a graph paper, that we were given back in school, a sheet of horizontal and vertical green lines. And we would be presented with the problem, and essentially we'd have to use the graph paper to plot the problem in terms of a chart, right? So this is the line chart that you're seeing, on a piece of graph paper. But this is not the graph that we're talking about here. When we talk about graphs, we're essentially talking about a network, right? So we're talking about what you see on my left, which is essentially a network of connected entities. So the dots that you see in the graph are essentially the entities, and the links connecting them are, the relationships between them, right? So that's what we're going to come to. But of course, we'd like to know where all of this started, right? We need to understand what a graph is, but how did this all come into being, right? So where did this all originate? And who really thought that, a graph is essentially a network? So it all started way back. You wouldn't believe this, but it started way back in 1735. And this, it's essentially started with the problem of the 7 bridges of Königsberg. Now, what was this problem? Well, Königsberg was a city in Prussia, and this city had a unique topology, right? So this city was essentially, divided into 4 land masses by a river flowing through it, and there were 7 bridges connecting these 4 land masses. And Leonhard Euler was a famous mathematician, astronomer, astrophysicist of his time, and he was presented with this problem, this unique problem of optimizing a traversal through the city of Königsberg by using the bridges, but not having to cross a single bridge more than once. right? So this was the problem given to Leonard Euler, and he had a very unique way of looking at this problem, right? So he didn't want to be distracted by the river and the land masses and the bridges and all of that. So what he did was he tried to look at the geographical topology, and he tried to convert that topology into a network topology, right? So what he did was he represented the four land masses here as vertices, okay, and the bridges connecting the four land masses as edges. And he concluded that in order to solve for this traversal problem, well, you had to have either none or exactly two vertices with an odd number of connections to them, such that you could enter through one vertex and leave through the other. So that is what his conclusion was. And unfortunately, in our problem here, we see that every vertex here has an odd degree or odd number of edges connected to it. And unfortunately, there wasn't a way to solve for this problem, right? But nevertheless, Leonard Euler ended up inventing graph theory in the process. So it was a win-win situation in the end. It was back here where the foundation for graph theory was laid down, right? So it all started way back in 1735. So fun facts, well, Neo4j was not the inventor of graph theory, and nor were we the inventors of the graph database, but we definitely were the ones to popularize graph theory. And we were also the ones to put the word graph before databases, right? So we indeed created that space for graphs, in the whole field of databases. Right. So if you do a simple, Google search on entity relationship diagrams, this is what you're going to get, right? And every diagram out here that's listed is indeed a graph, right? You see a bunch of entities, and it doesn't really matter how they're represented as tables or whatever it is as flowcharts. But if you look at them, they're all entities and they're connected using relationships, right? So every entity relationship diagram in that sense is typically a graph. Right. So now that we understand what is it that we really call a graph, let's look at why are they so amazing, right? So why are graphs amazing? And let's look at some real world examples that have had impact, in the world. The Panama Papers is something that I guess all of you would know or probably might have heard of. It's not too far away from where we stand. But nevertheless, this was one of the biggest leaks in the history of investigative journalism, right? So what was this all about, right? And what did this have to do with graphs? So the Panama Papers was about, this whole corpus of legal and financial records amounting to almost 11 million and about a couple of terabytes of data, which was made available to this team of investigative journalists, right? And what they did was, they extracted the information from this corpus and they managed to model it as a graph, right? So information in terms of entities, company names, addresses, locations, actual people's names. So all of this was put together in a graph. And essentially, what was done was, the links between all of this was studied, and shocking revelations were made. Right. So this study was something that rocked the world because of the findings and and disclosures that came out of this investigation. So this essentially covered about 200,000 offshore entities. What really stood out was that these entities were actually linked to real people in the world, and these were people in influential positions, right? They were people, they were billionaires, they were politicians, and they were sports people and celebrities and all kinds of people in influential positions who basically used these offshore entities as their tax havens, right? So this investigation ended up exposing a lot of crime, corruption, wrongdoings in the network. And it essentially also led to, people having to step down from their positions as a result of these findings, right? So they were made accountable, they were made answerable for their actions. And this, what you see on the screen here, is the model behind the Panama Papers. And you might say that, yes, I mean, this looks to be a pretty simple model, right? It only has a bunch of entities in terms of the officer, the intermediary, In fact, they could just be the same thing. Then you have you have an entity, you have an address, and that's about it, right? But this model was powerful enough to find, those links which were not visible by just staring at plain documents, right? So by putting it into a graph, these links were made visible, and these findings were published. So yes, I mean, things like this happened. We had the Prime Minister of Iceland who had to, relinquish his prime ministerial position on account of the findings that were made. So this had a huge impact in the world, and this was just the start of investigations, because what followed was, the Paradise Papers in 2017, and very recently the Pandora Papers in 2021. Right, so all of this, all of these investigations were the result of looking at the data differently, right? Looking at data as a graph, and being able to find these missing links which were not really otherwise visible using, any other means. So, if you want to know more about the entire investigation, well, the ICIJ is the website. You can visit the website, and you can find out everything, about the investigation. But more importantly, if you're interested in the offshore leaks database at large, well, this is also something that's available on the ICIJ website. So you can, get access to this entire database. You can search for information out here. But more importantly, what you need to realize is that this entire database is powered by Neo4j, right? And it's essentially the database behind all of this information. We also have a sandbox, I think, on the offshore leaks database, and I guess the Paradise Papers as well. So if you're looking to explore any of these data sets, they're freely available on Neo4j, sandbox as well. Right. Now, another example of where graphs have had a very positive impact in the world is the Covered Graph project. Now, I know we're all behind the pandemic, but this project gained a lot of prominence during the peak of the pandemic, and essentially this was a project that was put together by a group of individuals. So they came together, to work on a common cause, and the common cause being, how do we make information around the family of coronaviruses available, easily accessible to people who are looking for it, right? So this was a team of, software developers, data scientists, medical professionals, people in the research field. So they came together, and they essentially worked on getting data together, right? And this data had everything to do with patents, research papers, clinical trials, medical treatments, everything from the biological data in terms of molecules and genes and functions. So essentially everything that had to do with the family of coronaviruses was something that this team worked on, and they essentially modeled all of this information in the graph. Again, they used Neo4j as the database. And what they also did was not just putting everything into a graph, but also providing resources to query and explore this graph, right? So that was something that they also did, which was really nice. And all of this is again available on their site. So if you go to this website out here, you will see the entire graph. You will also look at the applications that are available for you to explore this graph, and some of them are actually dev tools from Neo4j that we will look at in this workshop as well. And you'll also happen to see all the data sets that were brought together and essentially modeled as a graph. So again, a great project where it has had very positive impact in the world. And this is also an example of graphs for good, right? So if you are interested in knowing other examples of graphs for good, please visit neo4j.com, graphs for good, and you'll see a whole lot of real world examples out there where they've it simply had a positive value and a global impact in the world. Right. So these were two examples, but of course there are plenty more. And this is the model that I was talking about, and it's all available on their website. If you are interested, you can always visit the website and browse through it. Right. Now that we've seen, what our graphs and a few examples of, how they've had an impact in the world, we're going to leave you with a few guidelines, for you to recognize graph-shaped problems, right? So how do you really understand that, the problem sitting in front of you can be solved by a graph database, right? So some of these guidelines are going to help you with that decision. Right. So let's come to the first scenario here. So this is a question that we essentially need to ask ourselves. So does the problem, involve understanding of relationships between entities, right? And you might say that yes, everything is connected, but how do I make that decision? This is a very simple example where we're talking about purchase patterns between customers, and essentially we're trying to study purchase patterns so that we could then detect a pattern of interest and then probably recommend that purchase decision to another customer sharing common interest. Right, so this is something to do with recommendations, and I think we're not strangers to recommendations because recommendations is something that we find in almost every aspect of our lives. We're constantly being recommended, to do stuff, to what do we eat, what do we wear, what careers should we pick up, what's the next course I should study. So at every step of our lives, we've been recommended, right? And most of these recommendations are also sometimes unsolicited, but at the same time, we've been presented with so many recommendations. So recommendations are something that you can easily do with a graph. That's because when you study relationships in a graph, you can easily make inferences, right? So recommendations are basically relationships or links in a graph which do not exist, but something that you can infer from what you already see connected in the graph. Now, fraud detection is the exact opposite of this use case. So, in terms of fraud, well, you're looking for links that are there but should not exist, right? So, the Panama Papers was one example where there were links, there were hidden links, but those links weren't really easily visible, right? And those links were made visible by trying to understand the interaction between several entities, right? So fraud is again, we would say it's just two sides of the same coin. Recommendations, we're talking about links that don't exist, but frauds, we're talking about links that probably should not exist in the real world. Entity resolution is again something where graphs lend themselves very beautifully to. And it's all about, bringing data from various sources into your graph and trying to disambiguate entities, right? So how do you say that, two people in the graph are one and the same, right? So how do you understand that they're same? So what you could do is possibly take their various identities and try and see if there's any similarity that you can draw between the two, right? So you can disambiguate entities very easily in a graph. Data lineage is again one area. Most of you are software developers joining the session, I assume. So when you're talking about data lineage, we're talking about data flows, data pipelines, and typically, we would have data flows where data originates from the source and finally finds itself in a destination database. Right. So when you're studying data flows, you would want to see what are the transformations each data point has undergone, during its course from the source to the destination. And this data lineage is something that you can, you can model very easily in a graph, and you can understand, dependencies, right? So taking a source data point, you can understand, where all, it has probably been used in what all destinations, whether it's a database, whether it's a report, whether it's an application, whatever it is, and also the reverse, right? So all these dependencies and the interplay between all of these can easily be seen if it's modeled as a graph. Social networks, well, I don't really need to say much here because social networks are, just self-explanatory, right? So they are just inherently by design a graph, right? So we all know that everything that we, feel, think, say, do is somehow, impacted or somehow influenced by our connections, right? Or the people in our network. So social graphs are, they're just graphs inherently, and putting it in any other way would just not make sense, right? So I think that's something that's a no-brainer. It's a graph by design. This is the other question that you can ask yourselves. Does the problem involve a lot of self-referencing to the same type of entity? Now, in this example here, we're talking about a typical organizational structure or organizational hierarchy where a person reports to a person, reports to a person, right? Or a person manages a person and manages a person, and so on. Now, if you see such graphs where you see repeating entities and relationships between the same set of entities, well, then this can also be modeled very beautifully in a graph. And there are other examples of this, like identity and access management, where you're trying to look at users and groups and roles and privileges and trying to understand inheritance, and essentially just access management in general, right? So this is again a use case which can sit very nicely in a graph, and you can query all of this information very, very easily in a graph. Social influencers and friends of friends are again the same thing. They're all basically they're just subsets of the social network, and once again, they're just inherently a graph. Well, this is the other guideline where we talk about, do you have, entities where you don't really understand how deep they are, right? In terms of the relationships connecting them. So if you have relationships of unknown or varying depth, well, then this is again something that you can put very easily into a graph, model it into a graph, and then you can query this information that much more easily, right? And this example out here is one where we're talking about a typical, it's a part of a supply chain, not exactly a supply chain, where we're talking about suppliers and we're talking about retailers, right? But if you really look at a supply chain, well, with the introduction of each additional layer of, entity or complexity, the supply chain increases in terms of complexity, right? So how do we make a supply chain more visible? And when I'm talking about visibility, I'm talking about well, how do we understand, what are the sources of the ingredients that are used in manufacturing a product? And when I say ingredient, it could be a part, it could be a material, it could be anything, right? So in a typical supply chain, you would have a source, you would have, manufacturer, manufacturing something, you would have suppliers, and on the consumption side, you would have retailers, and then you would have the end consumers, right? So how do you understand what is the interplay of each of these entities in the entire supply chain? Typical use cases would be, how do you trace a particular source of material all the way to its finished product, right? And another use case could also be, in case of, products which have been manufactured with a defect. Well, how do manufacturers understand in which all markets their products have been supplied so that they can then end up recalling the product, right? So how do you bring about visibility in your entire supply chain network? So this is something that again can be solved very, very well with the graph. Bill of materials is again something on the same lines, in the sense that you're trying to understand parts and subparts and assemblies and communities of parts which ultimately end up being used in the manufacturing process of product, right? So what are the quantities that you would require of each of them in order to produce a particular product, right? So once again, this is again in the same lines, and you can model all of this very well in a graph. Network management is again for organizations who probably manage their own network and IT assets. Well, you can put all of this in a graph. You can understand what IT services are running in which data centers, and what is the networking around in those data centers. And say, for example, if you're trying to understand the impact of one component being down in your network, well, who are the end users who will be impacted because of that, right? So if something goes down, say a data center goes down, or say a server goes down, then how do you really map the services that are running on those servers, right? How do you identify who are the end users who are impacted? So all of this dependency tracing can be done very beautifully in a graph. Routing is again one example where you're basically just trying to understand, what's the, best way to get from point A to point B. And finally, this is the last guideline where we're talking about, does our problem involve discovering lots of different routes or paths that are available, right? So, for example, in typical logistics and routing problems, also in a supply chain, there are several routes to get from one point to another, right? So, in terms of the supply chain, you have air routes, and you have land routes, and you have sea routes, and there are just so many routes that you can take to get from one point to another. But what's the best way to ensure that you transport a container containing your goods from point A to point B, right? So logistics and routing is again something that can be solved with a graph. Infrastructure management is again the same thing that I talked of. And of course, dependency tracing, like I said, dependency tracing is actually, a broader use case that can be applied almost everywhere, right? To trace the dependency of one component on a subset of components. So these are some guidelines to help you understand where graphs, can play a good fit. Just because you have a graph database doesn't mean that it can solve for everything out there. It's meant for specific problems, and it definitely takes a while for you to understand whether it's a good fit. But nevertheless, these are guidelines to help you with that decision. Right. So now that we've seen a few guidelines to help you understand where you can actually employ a graph database to solve what you're trying to solve for, we will now jump into Neo4j, which is essentially a graph database. And we're going to look at what is Neo4j's implementation of a graph, right? So this is essentially called a property graph model, and Neo4j invented the property graph model. It's one of the ways in which you can implement a graph database. So let us look at what the components of this property graph model are. Right. So we start with nodes. And if you remember the 7 bridges of Königsberg problem, the network model essentially had vertices in it, right? So nodes are nothing but vertices. We don't call them vertices because we don't want to scare people, and we don't want to use mathematical terms. So we call vertices as nodes. And what are they? Well, they are the basic building blocks in a graph, right? So without nodes, there's really nothing to connect. So you need to have nodes to start with. Now, what do they represent? Well, they can represent anything of interest to you in a given domain. So they can represent entities or objects or whatever it is that you're trying to represent in your graph. You can group nodes together and label them. And this is essentially, to kind of classify nodes in groups. And what you can also do additionally is that you can assign more than one label to a node. Now, this is a little different when you compare this to the traditional, RDBMS world, where every row belongs to only one table, right? So if you try to equate a node to a row, well, in that sense, a node can actually have more than one label assigned to it, right? So I'll be drawing parallels here and there to relational databases, but that's just, since most of you might have worked with a relational database, I think this might help. A node can also additionally have properties on it, right? So you can add extra information to a node, or you can enhance what you're trying to describe of a node by adding properties to it. So in this example here, I am representing my node by a label called person. And this is how you essentially represent it in Cypher, and we're going to, of course, see the syntax later. This is basically what I'm trying to depict here is an instance of a person, right? So I'm depicting this node as an instance of the person label, and I'm attaching a set of properties to this node. So this node is identified by a name. Basically, the name is Jane. I have also an age and a Twitter handle property to this node, right? So in Neo4j, a thing to understand is that we don't really have anything like a schema. So what we do in Neo4j is we do something called as instance modeling, right? So I have a person entity in my graph, but I'm trying to represent the person entity as an instance, right? And what I'm drawing here on the screen is exactly that. It's an instance of a person, okay? The next is relationships. Well, without relationships, there wouldn't be a graph as well, because relationships is what, it's basically the center of everything that we do, right? Now, relationships are also called edges. Again, we don't use the term edges, we use the term relationships because relationships are what matter. And they are used to connect the nodes in our graph, right? So essentially, they add structure to the graph. They are first-class citizens in a graph, and which is what makes it so unique from a relational database, because these relationships are actual physical links that are written to the database, right? So they are not hidden in technical metadata as it would be in a relational database, right? So these are not foreign key constraints; these are actual physical links written on disk and also present in memory, right? So basically, they are called first-class citizens. Why? Because we give them equal importance. They are part of the business data in your graph. Now, relationships always must have a type and direction. Well, the type is nothing but a name given to the relationship. So how do you really how do you explain the relationship? Right? So you call it by a name. So in this example here, owns is the name of the relationship, right? So I have two nodes essentially, a person and a vehicle in a car node. Like I said, a node can have more than one label. So vehicle is the broader label or the broader category, and within that I have a car, right? And owns is essentially the name of the relationship connecting the two. Now, relationships always must have a direction as well. Now, direction simply implies the flow, right? So basically, what are you trying to connect to what, right? So here I'm trying to say that the person owns the car. So the car does not own the person, right? So, which is why we denote always a relationship by a direction. Now, additionally, relationships can also carry properties on them. So, in this example here, I'm assigning a property called since, and the value of the property being 2011, right? So, what I can do with relationships is, I can qualify a relationship or I can quantify it by using a property on it. Now, nodes can also have multiple relationships between them. So in this example, I have just one relationship between the two nodes. But say, for example, if the same person also happens to drive the same car, well, then I could have another relationship called drives between the two, right? So that is possible. Now, what you need to understand in Neo4j is that a node can exist without relationships, right? So you can have, nodes which are islands, lonely nodes by themselves, which really doesn't make a lot of sense in a graph because you would want to see things connected, but it's still permitted. But the other way around, relationships which are dangling are not permitted. So you can't have dangling relationships in Neo4j. So relationship always has to have a node on either end of it, right? So a relationship without nodes is not permitted. And lastly, we have properties. And yeah, property, we use the word property in the property graph model, so they have to be there. So properties are something that add color to the graph, right? So basically, they are used to describe nodes, they're used to describe relationships. And they enrich nodes and relationships with additional information. Now, when used in a relationship, like I said, they are used to qualify or quantify the relationship. Like, say, for example, if I have a relationship between a person who has reviewed a movie, well, then I can also assign the rating or, probably the rating on the relationship, right? To quantify how strong that reviewed or that review, of the movie is, right? So I can assign values to quantify the or basically qualify the relationship. So these can be integer values or these can be text or whatever it is, right? So for you to understand the strength of the relationship. And properties are essentially key value pairs. So they're always represented as key value pairs. If you look at this name, Jane, age 21, Twitter handle, whatever. Also on the relationship, if you see since 2011, well, they're all key value pairs. Now, the last point is something to remember and to understand, because this is, again, a huge shift from how relational databases work, right? So in a relational database, you would first of all have to define the schema upfront, right? So you would have to say create table, whatever, with all these columns, and you would have to fix the table schema before you even try to load data in it. Well, in a graph, like I mentioned, in Neo4j, we don't really have any predefined schema. That's one. And the other thing is that you don't have to have the same set of properties on nodes belonging to the same label or on relationships belonging to the same type, right? So you can have an uneven distribution of properties, and this is simply because in the real world you might not really have a value identified with that property, right? So if you don't have a value defined on that property, you don't just have to store it. You can just completely ignore it and just don't store it on the node or the relationship, right? So for example, here, if I say, if I'm a person in the graph and I don't have a Twitter handle, and I really don't have a Twitter handle, so then I would not have a Twitter property on my node in the graph, right? So that is how my node would be created. And this is again something that baffles people, because they don't seem to understand this enough. But that's how it works in Neo4j. So if something doesn't exist, you just don't create it, right? So that's how it works. So finally, to sum up the property graph model, well, this is what we have as the components. You have node labels, you have relationship types, you have nodes, relationships, and properties. Right now, since we've seen what the property graph model is all about, I think we're ready to try our hands, querying the graph and understanding what this is all about and how all this comes together. So we're now going to look at Cypher, which is essentially Neo4j's graph query language. Okay, it's a language which was, by the way, invented by Neo4j. It is purpose built for graphs, right? I'm sure when we started off with Neo4j, we didn't really have a query language back in the day. And of course, I'm sure we would have looked at all the options available before us, and nothing came close to a language which was meant for graphs, right? And that's how Cypher came into being. And Cypher is essentially a pattern matching language, right? So one thing that you need to understand in a graph is that in a graph, there are no rows and columns, right? We're not talking about rows and columns anymore. We're talking about, if it's a network, we're always talking about paths, right? And to query the graph is actually to match a pattern in the graph and query that pattern back, right? So this is a huge shift again from relational databases, because we don't think in terms of rows and columns. So we're always thinking in terms of paths. And essentially, Cypher is a pattern matching language in that sense, right? So you always match a pattern and then you query elements from it. It's a declarative language, and the reason we call it declarative is because we focus on what do we really need from the graph. We don't focus on the specifics of the job, right? So we don't really tell the graph how to do a particular task. We just tell the graph that this is what I need through a Cypher command or through a Cypher query, and the graph will return that back to you. It's a very expressive language, and we will see, when we have a look at the basic syntax, we will see that Cypher is expressive. It uses ASCII art. And this is, again, it adds to the whole elegance of the language. It's also built to be easily understood by not just developers, but also business users alike. I'm sure that, if you took a SQL query to a business user and tried to explain it to them, I'm sure they wouldn't really get anything of it, right? But you can still do the same with a Cypher query, and I'm sure business users will still be able to appreciate and understand what's really happening in the query. And the reason behind it is because, the query actually represents the way you draw your entity on a whiteboard, right? So when you write a query, it really represents the whiteboard model. So in that sense, it is something that is built to be easily understood by business users as well. And finally, if you're still looking for reasons to learn Cypher, well, this is where you should stop, because Cypher is contributing to a standard for graph databases in terms of a language in a big way. Just as we have SQL for relational databases, and SQL was basically devised by this community, the ISO community, of people who came together to form a standard. The same community is also working on a standard for a graph query language, which is called as GQL, or GQL. And Cypher is contributing in a very big way to the syntax that will soon come to be part of GQL. Right. So if you learn Cypher, and if you invest time in learning Cypher, I'm sure it is going to take you a long way, because when GQL comes out, you'll definitely be there already. So this is just a screenshot of what our syntax in terms of a reference card looks like. It's available on our website, and of course, you can always have this handy as a reference available for you when you're coding in Cypher. But for now, let's follow along. Let's write some Cypher and let's understand how we can query the graph. We've already loaded data in our graph, so let us look at some basic syntax as to how we can query the graph. Okay. So I'm hoping this link will be shared in the chat. And now we can go back to our Aura instance. I'm hoping that the Aura instance for all of you is up and running. So what we need to do here is essentially we have three options, that we provided with our AuraDB. So one of the options is to query the graph using an interface called as Neo4j browser. So browsers is essentially a web page, a single web page application which can help you write Cypher queries either to load data or to query data from the graph. So we're going to start with this, and then we're going to move on to the other two options. So I'm going to launch my browser, and well, it needs the password that you originally were presented with when you spun up your instance. So make sure that you have saved the password securely somewhere so that you can then connect. Right. So when I connect to my instance, this is what I'm going to see. This is what I'm presented with. What I can see here is I can see the number of nodes and the number of relationships in my graph, right? So I'm seeing that I have two labels in my graph, which is essentially the movie label and the person label. And I have a bunch of relationships, and these are the types of the relationships that are existing in my database. Now, if I quickly want to see what the model looks like, this is essentially data, but if I want to see what the model looks like, well, I can issue something like called db.schema.visualization. It's an inbuilt procedure. And if I fire this command, well, this is what, it'll bring up, right? So, essentially, this is what the model looks like. It's a very simple model. So I have a movie label, and I have a person label, and I have a bunch of relationships connecting the two, right? So this is the simplest model that we use to teach Cypher to people out there. But yeah, this is what the model looks like. Now, if I want to query the graph, if I just want to see, randomly what are the nodes in my graph, well, I can issue a statement like this. I can say match in and return in, right? So what does this do? Well, match is actually, like I said, everything in a graph is a pattern, right? So we're always matching on a pattern, and we're returning, either specific elements from the pattern or whatever, or the whole pattern by itself. So here, this is how we represent a node. So we use parentheses for nodes, and if you actually look at it, if you bring the parentheses together, it will represent a circle, right? So this is essentially how you would draw the model on a whiteboard. So you draw your entities, you represent your entities as circles on a whiteboard, and this is essentially the ASCII art that we were talking about earlier. So if I run this, well, this is what I will see. So essentially, it brings back, it brings back a whole bunch of random nodes. Okay, and they already seem to be connected, right? So you might say, well, I only asked for nodes. Why am I getting back, these relationships as well? So this is owing to a setting in the browser application. And I'd just like to show you what that setting is. So if you go to settings in browser, you will see an option, that says connect result nodes. right? So what this does is, if you ask, for random nodes, or if you only return nodes in your, in your Cypher query, what browser does behind the scenes is, it kind of tries to run another query on top of what you're returning, and tries to understand if there are any links between the nodes that you're returning in your result set. And if there are links, well, it will show up in the graph view. Right, so this is just to excite people about graph views, because we don't want to show boring results to people. So we kind of color it up, we kind of make it a little more impressive by showing a graph view in the result. So if you don't really wish to see this, and if you only are interested in seeing what you have asked for, well, you can just uncheck this option, and and then you will just get random nodes. If I uncheck this and run this again, well, then I end up getting only nodes, right? So I don't have the relationships between them anymore. Right, so I'm going to keep this checked for now. Now you might say, okay, this doesn't make a lot of sense, because I'm only seeing random nodes here. What if I'm interested in only fetching nodes of a particular type, right? So say, for example, if I only want the person nodes to be returned, well, then I can do something like this. I can say, fetch me just the person nodes just belonging to the person label, and if I run this, then I just get person nodes. So what I can additionally do is I can click on node, and I can also see its properties. So a person node in my graph has two properties. It has the name, and it has the year of birth of that person. I can do the same thing even for movie, because I have a movie label as well. So if I hover on a movie, well, I can see its properties. So basically the title of the movie, the release year of the movie, and the tagline is what is stored in my graph. All right. Now let's go one step further. Now this is about, again, returning random nodes. What if I'm looking for a particular node in my graph? Like, what if I'm interested in only fetching a particular node, and I know I know how to narrow down on that node. So let's look at searching for, say, Tom Hanks. So this is how I would do it, and there are a couple of options here to query a particular node. So I can say, fetch me a node where the name is Tom Hanks, right? Because I know that I'm looking for Tom Hanks. Now, if I hit this, run this, well, I'll just see, it fetches me just one single node. And of course, I can see the properties of Tom Hanks. Now, there are a few ways to write this. This is one way in which you can write such syntax, but I can also pull this out and introduce a where statement here, right? So I can say where n.main equals Tom Hanks. Okay. So just to draw parallels again with SQL, because just in case you're already familiar with SQL, well, the where clause in Cypher is exactly the same as it would work in SQL. So you use where to filter the results. The match is essentially, like I said, we always start a Cypher query in most cases with a match clause, because we're always trying to match a pattern in the graph. But match is the equivalent of the from clause in SQL, right? So when you say select something from a table or whatever, a bunch of tables, well, that is the equivalent of the match here in Cypher, because you're always saying this is what I need from the graph, right? Match on this and then fetch me whatever. So return is essentially the equivalent of the select clause in SQL. So we've taken away your precious select. We don't have the select clause anymore in Cypher, but everything that you specify after the return clause is essentially what you want is part of your result set, right? And your return clause is essentially a clause where we give you complete freedom. Well, you can just query about anything from the graph, right? You can query any graph element, portions of it. You can add your own, custom data to it, whatever, right? So you can return basically just about anything in any structure, be it a list, be it a map, whatever it is from the graph. Now, there is one more way how you can do this, and basically this is the way. So you can actually have the where clause inside the parenthesis itself. and this would also work. Okay. Now, you might ask, is there any, edge in terms of performance in the way you write these three different constructs, right? So we've written the same query in three different ways. So you might ask, is there, does one perform better over the other? And there's a trick as to how you can determine that. So you can always profile a Cypher query, and you can look at the execution plan generated. And if the execution plan is similar, with the same number of dB hits. So we use the term dB hits to measure the cost of the plan that is generated, or essentially it's the amount of work the database had to do in order to fetch the results back to you, right? So if a plan looks to be the same, well then essentially the queries are the same. So there's no advantage of writing one style over the other, because the underlying plan that's generated is finally one and the same. Okay, and you can try that out. You can just use profile before the query, and the plans that are generated for all the three that we've tried so far will essentially be one and the same. Now I'm not going to do that. I'm just going to move on to other things that we can do. Now, let's look at something else. So I'm going to go back to a query where, say, let's now try to extend our pattern, right? So far our pattern had only one element to it, which was essentially the node. Now let's try to extend this pattern and see what we can do with this. So essentially, I'm looking for, say, all the movies that Tom Hanks has acted in. So what I can do is I can etch those, okay? And this is a way how I can actually fetch the movies that Tom Hanks has acted in. So acted in is basically relationship type in my graph. And what I'm trying to say here is, fetch me all one-hop patterns where Tom Hanks happens to be the starting point from the graph, right? So this is how I would represent it. And maybe I just want to return the number of, such patterns that exist. So I'm just going to do a basic count. So count is again the equivalent of what you have in SQL. It's used to count. But in case, in this particular use case, I am counting the number of patterns here. So that's something to keep in mind. So if I run this, well, I get 12. And essentially what that means is there are 12 patterns where Tom Hanks happens to be the starting point. And we don't really know what is at the end of it, but we do know that there is an acted-in relationship for each of those patterns, right? So that's what this means. Now, if I want to see this graphically, well, I can assign a variable to this entire pattern, and I can just, return this path, and I'll be able to see, well, indeed, there are 12 movies that Tom Hanks has acted in. But additionally, I see this directed relationship also showing up. And that's again because of that, co-op that I talked about in browser, wherein it brings up, it shows up additional relationships that might exist between the nodes that you've already asked for. Okay, so once again, this is just a browser trick. So if you don't really want to see something that you've not asked for, well, you can go and disable the setting and you'll be able to see 12 relationships. Now, let me go back to the same example. So once again, I'm talking about counting here the patterns. So if I run this again, I get 12, which are 12 movies. Now, there are a couple of ways you can rewrite this. So I can totally leave out the relationship type here, right? I can totally leave out the relationship type, and I can run this. And now I get 13. Now, why is it that I get 13? Because there are 12 movies where Tom Hanks has acted in, and there is also a directed relationship to one other movie, right? So I get 13 patterns in all, where Tom Hanks happens to be the starting point, because I haven't specified the relationship type, which is why wherever Tom Hanks happens to be the starting point in my graph, well, those patterns are returned back to me. I can also leave out the relationship direction altogether and query, and I still get back 13, right? So this is another way to do it. I can take out the square brackets totally. So the square brackets are essentially how you represent the relationship type. I can take out the square bracket notation. I can just say that, I know that there is a link between Tom Hanks and, some nodes in my database, but I don't really know what the relationship name is linking the two. So I can simply indicate that by, a hyphen hyphen and run this, and I would still get 30. Right. So these are different ways in which I can represent relationships. So I can represent relationship by the actual type within square brackets. I can leave out the type, or I can just use a hyphen notation to say that something exists, but I don't quite know what it is. But please return, the patterns back to me.
Priya,
all right.
can we do a quick pause? And I think a couple of people are struggling with setting up their AuraDB instances and choosing the movie graph. Maybe if you could go back to the instances view and show people in a or maybe start a new instance and so people know exactly what to do and what to click, so we can make sure that everybody clicks the right thing. When
Okay, so what I can do is maybe I go back to my slides, because I would not be able to destroy my instance because that would again take me a while. So this is what
I meant if you click on new instance, you get the thing that people can basically select.
Okay. But I wouldn't get that because
of course, yes.
Yeah, created a free instance. So I wouldn't get that option. But I can take you back to the slides. Let me just do that. So when you click on new instance here, you should see something like this, right? Because if you already don't have a free instance created, well, then this is a screen that you'll be presented with. And what you need to do is choose the movies option here. And once you click on the movies option, you'll get a create button on it. And all you need to do is just click on create, and that's about it. That should create your database and load the database with the movies data. So if you already have the database running but you don't see the data loaded, well, then what you can also do is you will have an option to load a data set. For those of you who don't see any data in your instance, well, you also have an option to go to load data set on your database, and there you can actually choose the movies graph, and that's how you can get data loaded. So that's the other way to do it. So can we know what exactly is the problem? I mean, are people having...
I think that was good. Just a recap. I think a couple of people had struggled. Probably set up an empty one, or some people say the movies don't populate. So I think we got a way around, and I hope that works for everybody now. And
Yes,
if you don't, it's another thing maybe to remember: user and password. Username will always be Neo4j. Password is randomly generated, so you will get a little prompt that tells you save this password. If you then click on OK and don't save the password, then you have to destroy your database and set up a new one.
Yes,
there's no way of recovering that.
That's true. Yeah, that's true. So please make sure that you save your password securely, because the password is also not known to Neo4j. So if you don't have the password, well, then you got to start all over again, destroy your database, and spin up a new one.
Yeah, and it just takes a couple of minutes. So be patient, and then it gives you a little. Can you go to your instances view again? So then you see.
Yeah, you'll see this
preparing, and then it says online when it's ready.
Yeah, that's right. It'll say running when it's
online. Running. Sorry, yes, it says running. Yes.
Yeah. And this is what you will get if you load the data set manually. So if you see your database running but you don't see any data in it, well, no worries. You have an option here, in this ellipsis. If you just click on this ellipsis button, you'll get an option to load data set. You can click on that and choose the movies graph there. So once you do that, it'll show data loading, and then it'll be up and running with the data that we are trying to query.
Okay.
All right. Cool. So please try this.
I hope that gets everybody up to speed. No worries, you didn't miss much. We just at the beginning, and then we can continue. Thank you, Priya.
All right, no problem. Okay, so I go back to my browser. And now what I'm going to do is I am going to just, in the interest of time, I'm just going to copy the queries from the wiki link that's posted. So I'm not going to do everything, but I'm going to do some of them, just to take you through the syntax. Right. So let us try to fetch elements, from the graph. So what we can do is, let me close all of this. Right. So now if I'm interested in fetching specific elements from my graph, and I'm not interested in the whole path or pattern or whatever it is, well, this is how I can do it. I can assign variables to, all the elements in my match pattern, and then I can extract what I need from it, right? So in this query out here, I'm saying again, fetch me all the movies that Tom Hanks has acted in, but I want the name, the roles Tom Hanks has played in the movie, and the movie title. Right. So if I run this, this is what I get. So essentially, I get Tom Hanks. Of course, he's repeated in every pattern because he's there in each of the patterns, right? So I get the same Tom Hanks property. I get the roles. Roles is essentially a string array on the relationship acted in our graph, which is why you get data which is visible like this as a string list. And then finally, you have the title of the movie, which I'm returning. Right. So I think I talked about counting patterns, but I think this is maybe worth one more try. Um, so in this query out here, I'm also trying to fetch, all the movies that Tom Hanks has either acted in or directed. And this is the way I can do it. I can use a pipe notation to say or, right, to denote or. So fetch me all the movies where Tom Hanks has either acted in or directed. And what I'm trying to do is I'm just trying to, fetch the count, right? So I get a count of 13, and we saw this count earlier as well. But what I want to highlight here is that it doesn't really matter what I count here, right? So if I say P, I still get 13. If I say M, well, I still get 13, right? Because what we're counting here is the patterns, right? We are not counting any specific elements. We're counting how many parts, one-off parts are there with Tom Hanks as a starting point. And that's essentially what it is returning back to us. Now, if you say that if you're interested in only understanding what are the unique movies that Tom Hanks has either acted or directed, well, then what I can do is I can fetch that by using distinct in my query. And then if I run this, I get 12, right? So there are only 12 movies that Tom Hanks is associated with, whether he's either acted or directed in, but there are still only 12 distinct movies. So I can use the keyword distinct here to fetch that result back. Right. So again, distinct is the same way as you would use it in SQL. It essentially works on a set of rows and finds a distinct of them. Now, a couple of other queries that we can try in our data set if we want to find out all the people who are directors in our data set. Well, this is something that you can do. So person directed whatever it is, movie, and fetch me all the directors. Now, oops, I see that, the name repeats here. I'm getting the same name multiple times. And why is that? Well, it's simply because the same person may have directed more than one movie in my graph, right? Which is why I end up getting the same person multiple times. So I can work around this. I can say, once again, use the word distinct here, and I can get unique directors in my data set, right? So if I just collapse the pane, I see that there are 28 people in my graph who are directors. Now, there are some other ways in which you can write this. Same thing, you can obtain the same outcome. And a couple of ways that you can do it is you can say, match me person where there exists a relationship between person and something, right? Where the relationship name is directed. Okay. And if I run this, well, I still get 28 directors, right? So this is another way you can use the where clause with an exist clause, okay? And you can put a pattern inside the exist clause to denote the same thing. So what this is saying is match me all person nodes where there exists a relationship, an outgoing relationship from that node to whatever node it's connected to. But I'm trying to represent that relationship using the directed relationship type. So this is another way how I can do this, and I don't need the distinct here because I am matching people. So if I run this without the distinct, I still get a distinct set. All right. So that's another way how you can do this. And of course, you have the option of putting the where clause inside the parenthesis itself. So you can rewrite the same thing with the where clause inside the person parenthesis, and it will still give you the same result. Now, if you want to take this thing one step further and find all the people in my graph along with the movies that they've directed, this is how I can write it. So what I can do is I can say person directed a movie, fetch me the name of the director and a list of all movies that he or she has directed. Okay, and the way I do it is I use the function collect. Now collect is basically a function that you can use, and the output of this function is a list. It's a list of whatever it is that you're trying to collect. Okay, so if I run this, this is how the output looks. So I get all the directors in my graph, which are essentially 28 in all, and I get the list of movies that they've directed. Okay, so this is a pretty cool way how you can fetch results from your graph, aggregate them. So collect is essentially an aggregation function, right? So it aggregates the results and brings them back to you in the form of a list. Right. So there are a few things that you can do here as well with aggregation functions. So what are they? Let's look at them. Right. So this is something that you can do. You can count and you can also collect at the same time, right? So once again, we're talking about people, but we're talking about people who have acted. Okay, I can take this out because I'm not interested in the matrix alone. So if I want to find all the people who have acted in a movie and fetch me basically the actor count and the people who have acted in the movie, then I can run something like this. And what I will get is I will get all the movies and I will get the actor cast in a list, and also the count of people in the movie, right? So I also get the count cast. Now there are again a couple of things that you can do with when you're collecting results. You can also order them, and you can try and fetch a part of them, right? So that's also possible. We don't have anything the equivalent of a group by clause in Cypher, but grouping happens implicitly by use of a grouping key. And I'm going to just show you a few examples of how you can group results in Cypher. So this is one of them. So what this query is doing here is, again, I'm talking about actors. So basically people who've acted in a movie. And then I'm trying to fetch the movie name, the year of release of the movie. And I'm trying to collect the cast, okay, of the movie, which are essentially the actors. And then what I can do is I can order by the cast, the size of how many people have been associated with each movie, and I only want to pick movies where I have more than 5 actors. Okay, so this is how I can do this. I can use something called as with. So with clause is essentially used in Cypher to chain the results of one match pattern with another, right? So when you have too many patterns that you're trying to fetch data from, well, you don't really have to put everything into one gigantic match clause. Well, you can break that into parts and use with chain the results of multiple matches. Okay, so in this example, I don't have multiple matches, but I am using a with clause here so that I can order the results. Okay, and then I can use a where clause on the ordered set. So this is the equivalent of saying group by having in SQL. We don't again have a group by, nor do we have a having clause, because the where clause does the filtering that is achieved using the having clause in SQL. Okay, so if I run this, I essentially get only movies where there are more than 5 actors in them. All right. So we've seen a few more clauses. We've seen how you can order by, how you can group by, first of all. So the grouping is implicitly done based on whatever grouping key you provide, right? So in this query, the results are automatically grouped by the title and the year of release of the movie, which is essentially the same movie node in my graph. And I'm just collecting all the actors associated with each movie. So the grouping is implicit. And if you want any filtering to be done on the group result sets, well, you can use the where clause, which is the equivalent of the having clause in SQL. Right. So, few more things that you can do. Now you can write the same query in this manner as well. You can match the movie. You can pick. You don't have to order by before you say that I want movies only where the cast is greater than 5. So I can bring down the order clause even as part of the return clause, right? So I can simply say group by having, which is basically my where clause here, and then I can return the same results and then order them by in the end. What I can also do is I can limit my result set by using a limit clause. So in this case, what I'm saying is still fetch me movies with only greater than 5 actors, but of that result set, only fetch me the top 3, right? Because I don't want the whole result set. So if I run this now, I only get 3 movies, and they are ordered in a descending fashion based on the size of the cast, and I get back only 3 rows in my result. Now, you may say you're talking about rows, but we don't have anything like rows. That's true. But since we are fetching specific elements of the graph here, well, then, the way the elements are represented are in the form of a row. So that's how we get back the results. All right. Right. So that was about grouping and how you can use order by along in conjunction with, a return clause, order by in conjunction with the with clause. And then you can apply limit. We also have skip clause in Cypher where you can skip a few rows and then limit your results, right? So it will skip a number of rows and then return whatever is there after, after those rows have been skipped. So that's also possible. Now, a few other clauses that I'd like to take you through quickly in the interest of time. Well, let's look at this one. So what is this query doing? So I, want to fetch all the people in my graph and want to associate a count to them with respect to the movies that they've acted in and the movies that they've directed, right? If they happen to have acted in any movie or directed a movie, I want the counts of those movies along with the person name. Now I can write it like this. I can just say match person acted in movie, get me the person node, get me the count of movie nodes, and then do another match with the same person node that's directed a movie, and then add the directed count as well to the result set. Now, if I run this, well, what do I get? I get only 5 people in my graph, but I see that I have a value in the acts column as well as in the directs column. So what does this tell me? It's only bringing back people who have acted and directed in the same, or basically who have only acted and directed in movies, right? It doesn't matter what the movie is, but it's only fetching me people where it finds a relationship to both acts acted in and directed in my graph. Now, this is not what I want, because I want a listing of all people in my graph with the counts if they happen to exist. So, we can work that around in Cypher by using a match clause, which is optional. And optional is essentially the equivalent of an outer join in SQL. Again, we don't have anything like joins in Cypher, or we don't have anything like joins in Neo4j. But this is one way of expressing an outer join in Cypher by using an optional match clause. So how you can do this is by using optional match in this query for it. You can say match person, and then you can say optional match the same person node to a movie node using the acted in relationship. Fetch the count of movies, and then again do an optional match with the same person node using a directed relationship, and then add the count of movies directed, right? So if I run this, well, what do I get now? If I just collapse the result, well, I get 133 rows or records in my result set, which is essentially the number of people in my graph. I have 133 person nodes, and for each of the 133 person nodes, I am getting a number if it applies to that person. Right? So this is one way how I can use an optional match, which is essentially the equivalent of an outer join in SQL. But there are a couple of other smarter ways how you can achieve the same thing, and they are by using a few additional constructs in Cypher, which is basically, one of them, which is called the pattern comprehension. Now, what is a pattern comprehension? But a pattern comprehension is a type of construct in Cypher that you can use, which is a little more efficient than what we just did, but it essentially achieves the same thing. So a pattern comprehension is expressed in this way. So everything that you put inside the square brackets is basically a pattern, and we're trying to extract a part of the pattern, and the results are essentially a list of what you get back. So what I'm trying to do here is I'm trying to match on a person node like I did before. And for the person node, I'm trying to, fetch the movies that the person has acted in. So this is basically the pattern, and I'm trying to extract just the movie node from it. And I do a size on the list because the output of a pattern comprehension is a list. So when I write something like this, well, this is the equivalent of an optional match plus collect, because it does an optional match and then it collects the results in a list, which is why the output of a pattern comprehension is a list. Okay, so I can use the size function on a list to get the size of the list. So this is a very smart way. I've just written, this is practically just one line of code. But if I write something like this and run it, well, I'll still get the same result. I'll get 133 people, and I'll get the counts where it applies. All right, so this is a very neat construct in Cypher, and it can help you do a lot by writing just few lines of code, right? And behind the scenes, it will still do an optional match and collect, but you don't have to be bothered about all those details, right? So it'll do, the query planner will take care of all of the specifics for you. So that was pattern comprehension. And this, by the way, is something that we teach in intermediate Cypher or advanced Cypher, but then this is just a better way of doing something, which is why I thought I should mention this to you. I'm not going to talk about count store right now. Let's do some patterns, okay? Now let's extend our pattern. So far we've been looking at nodes, we've been looking at just one relationship. Now let's extend our pattern a bit and see how we can play around with them. So this one is us, well, trying to see whether two actors have acted together with each other. And this is essentially a query where I'm trying to find out, has Tom Hanks acted with Tom Cruise in my graph, right? So what does the pattern look like? It says person acted in a movie, and then you have another person who's acted in the same movie, right? So this is how I can extend my pattern in my match clause to bring in or to express what I'm trying to look for. I'm trying to look for two people who have acted in the same movie together, and I'm also additionally trying to find whether two people have acted by assigning a name to the two person nodes. Now and then, of course, I'm just trying to fetch back the names, the roles the person has played, and the movie title. And if I run this, oops, I don't get anything because in my graph they don't happen to have acted with each other. Right now, if I change this to something else, maybe the usual suspect, Kevin Bacon, who happens to be on almost every movie. Well, then I do get a record. So I see that Tom Hanks has indeed acted with Kevin Bacon in my graph in Apollo 13. And these are the roles that both of them have played in the movie. All right. So this is how you can extend your pattern using the match clause, to do more. All right. And just maybe one more query, and then I think we'll move on to the other demos. So this is a query, which is a query where we're trying to, talk about a recommendation, right? So we're trying to recommend actors who can act with Tom Hanks. who have not acted with him before, right? So we're trying to suggest who can act with Tom Hanks in our graph. So this is a very, very simple query. I mean, you can see it's just hardly, just because I've kind of formatted it, it's like 5 lines of code, but otherwise it's hardly anything, right? So let's look at this pattern and understand what we're doing here. So we start the pattern with Tom Hanks. Uh, we are anchoring on Tom Hanks. And we're saying that, well, fetch me all the movies that Tom Hanks has acted in. And fetch me people who have acted with Tom Hanks in the same movie. So these essentially would be the co-actor lists, the co-actors who've acted along with Tom Hanks. And then find me movies that these co-actors have acted in. So essentially another movie node. And then find me co-actors who have acted with the co-actors in the same movie, right? So it's one long pattern, but if you really look at what we're doing here, where we are doing several joins, right? We're doing 1, 2, 3, 4, 5, 6, 7 joins. Okay, this would be 7 joins in a SQL query, but I have been able to do this, very simply just writing this match pattern in Cypher. Additionally, what I also need to do in my match pattern is I need to filter on a couple of things where I have to say that, well, this person, which is Tom, the Tom Hanks node, should not really be the same as the co-actor node, right? Because it's quite possible that, I might find Tom Hanks on the other end of the pattern, and I don't want that. So I'll have to filter that out here. And I'll also have to say that, well, Tom Hanks should not have acted with any of these co-actors, right? Because I don't want to recommend people whom Tom Hanks has already acted with. So these two conditions have to follow my match pattern for me to ensure that the result set is solid. And then finally, I just return the co-actor name here at the end of it. I also assign a strength in terms. So when I'm recommending something, I always want to recommend. I always want to order my recommendations as my top recommendations, right? So I'm trying to order on the basis of the common actors. So how many times has Tom Hanks acted with the common actors, so that I can then give importance or priority to that count. And that's about it. And I'm just collecting the common actors, and if I run this, well, this is what I get. So basically, these are the people that the query brings up. It is recommending, and you see Tom Cruise is also in the list because Tom Cruise hasn't acted with Tom Hanks yet. And these are the common, or you would say mutual connections, right, that Tom Hanks has. So essentially, you can get these actors to introduce the new actors to Tom Hanks, right? So they can be the bridge between Tom Hanks and people whom he has not acted with. So a very simple query, but nevertheless a very impressive query, because we've written it with only so many lines of code. And if you had tried the same thing in SQL, well, you can always try that out. But yeah, we're doing a lot in this query, and this is indeed a recommendation query. All right. So I think that's all that I will do as far as Cypher. And the wiki link contains a lot more. So I suggest that if you have the time, please go to the link. And of course, I can add more to this link. This link will be publicly available for you to use. So you can go back and try some of these queries in the same movies graph, and I'm sure it'll work for you. But for now, I would like to move on to the other two tools in the pack, so that you get an understanding of what else comes with AuraDB, so that you can then understand the usage of these tools, and then of course get into details into each of them. So let's do that. I'm going to move away now from the browser, and I'm going to go back to my AuraDB instance. And now I'm just going to show quick demos of the data importer tool and the data visualization tool. So in my movies graph, like I said, I launched the instance with a preloaded graph, right? So it already had 171 nodes and 253 relationships in my graph. And then you can see that here as well. So what I'm now going to do is I'm going to use the data importer tool to add a new data set, or basically to append to what I already have in my graph. All right. So what I want to say about the data importer is that it's a It's a low code, no code tool. In the sense, you don't have to write any code in the data importer. And it's also not a full-fledged ETL tool, right? So it's not supposed to be, or it's not meant to be looked at as a full-fledged ETL tool. So it's a tool for you to quickly get started to a point from your data to insights, right? So we don't want you to spend too much time loading data. If you have data sitting in a spreadsheet which you want to quickly prove in terms of the graph model, well, then this is the easiest option to get started with. You can simply use the data importer to load data into a graph and then get to a point where you can already start to query it, right? So in our use case here, the use case that I'm going to demo is the fact that I already have data in my graph, and now I'm trying to bring another source, which is again related to movies and everything that we've done so far, and basically append this data set to already what I have. All right, so let's do that. And if you want to follow, well, I think I have a link here where you can download the data. So let me just quickly go to that. Yeah, so this is the link where you can get the data from. This is again movies data. You'll have separate spreadsheets from where you can. This will basically just download as a file for you with with the spreadsheets of the movie data that we're going to be loading. So let me go back here and say click on import. So when I do that, well, I get back the same screen where I got to enter my password, and then I say connect. So this is the interface of the data importer. What I need to do here is I need to essentially draw a model. This is how I would generally start. I would draw a model, and then I would map the model to my source of data. And that's about it. And I just say run import, and it brings the data into my graph, which is a representation of the model that I would have drawn here. Now, in my case, I already have preloaded data in my graph, so I'm just going to append to what I already have. So I will start with adding a node, and that's how you do it. And since I have a person label and a movie label in my graph, I'm going to start with person. And now what I need to do is I need to select a file here. So for that, I got to first add a file so that I can then select it. I have to just search for it. Okay, so this is essentially the spreadsheets that you'll get when you download the movie data. And I have actually made a copy of the person sheet, and that's because I will show it to you in a bit. Well, in my data set, I have a born date, which is the date of birth of the person, and I don't want to add the date of birth in my graph because I just have the year for the born property. So what I've done is I've created a copy of the sheet and I've just extracted the year from the date of birth in my copy sheet. And now what I'm going to do is I'm going to map these additional set of properties to what I already have in my graph. So what I need to do for that is I need to select the sheet, and then I'm just going to say properties select from file. And I will say select all, but then I'm not going to choose the date of birth, and I'm also not going to choose the death date. All right. And if you see, my new source of data is basically an IMDb source. And I also have the name of the person in this sheet. So I'm just going to reuse the properties that I already have in my graph because I don't want to create duplicate properties. So I'm going to take care of that as well. So when I say confirm, I'm going to get all these properties out here. And like I said, I don't want to create duplicate properties. So I'm going to change the name of this column to born so that it matches what I already have in my graph. And I think I am good to go. Now here under ID, I will have to select a property which is unique to the node label so that the load can be done based on that unique property. Right, so I don't want duplicate nodes being created in my graph. So this is to avoid duplicate nodes from being created in your graph. So in my set, if I already say have a Tom Hanks, I don't want two Tom Hanks in my graph, which is why I'll have to specify this unique ID. And I'll choose the name here because that's what I have in my graph as already existing, and I don't want duplicate nodes being created. So I think that's about it. And now I'm going to just, what I'm going to do is go back to the browser and, just um, query Tom Hanks so that we can see what happens before and after. And I think I have a Tom Hanks in my new data set as well. So this is what I have currently before the import. And now what I'm going to do is I'm going to run the import and see what happens. So that's done. So I had about 444 additional people in my sheet, which is what has been created. And I think there was some comment, which is why only 415 nodes got created. If you want to see the query behind this import, well, this is what it looks like. Okay, and essentially we're using a merge clause to write data to a graph. Now, a merge clause is a clause in Cypher which is used to write data to the graph. Now, we didn't go over any syntax to write data, but essentially what this does is it will look for a node, and if it finds that node, it will not create it. If it doesn't find the node, it will end up creating the node. So it's the equivalent of upsert in SQL. It's pretty much that you find and then you simply update if you found the node. If not, you end up creating it. So let's go back to the browser now and select this one. And now you see that what has happened is the data importer has basically brought in additional properties on my Tom Hanks node. So I still have only one Tom Hanks in my graph. But you would see that, before I had only two properties, just the born year and the name. And now I have additional properties that have, that have been loaded in my graph. And this is essentially the biography of Tom Hanks. All right, so the same thing we're now going to do with movies very quickly. And if I just want to query a movie node as well, cast today. Okay, so that's not name, that's title. Yeah. So this is a movie node, and like I mentioned, I have 3 properties on my movie node. Now, I don't believe I have any common movies in my graph, but nevertheless, we're going to end up loading the movies as well. So what I need to do now is add another node, call this movie, in line with what I have in my graph. And now I'm going to have to add the movies file. And if you see, the movies file is again from IMDb and has a whole bunch of properties on it. But I don't believe I have any movies which are already common, like I had Tom Hanks, which was already there. But nevertheless, I'm going to end up loading this in my graph. So I'll select the movies file and I'll say properties, well, select everything. Again, I got to be careful of a few here. I think I already have a released property in my graph, and I don't want the date of release. I just want the year, which is already there in my data set. So I'm going to uncheck the released here, and I'm good with the year of the release. So I think I'll say confirm. And what I will also do is change the name of this here to released, because I already have a released property in my graph and I don't want duplicate properties being created. So I will change the property name there and then select the ID to be title, because I already have a title property in my graph. And I guess that's it. And now I run the import. And now I see that, nothing got created of the person because, the nodes were already created. So it just found it, it did a match and then it didn't end up creating anything because they already existed. Nevertheless, it did set the property values, because if it finds the node, well, it will then end up updating the node. So that's what has been done. And in case of movies, well, I got additional movies created, 93 and all, and of course, also their properties set. So I can now go back to my browser, and I don't believe I have anything common. So what I can do is maybe pick a property from here. say plot, and then just try to query the additional uh, movies that have been loaded. So and the way I can do it is I can say where plot is not null, because like if you remember, I can have properties on a bunch of nodes, which, I mean, if they don't exist for a node, well, then they won't be created. So if I have to pick movies where the plot exists, well, then this is how I'll have to do it. And if I run this query, well, these are all the additional movie nodes that have got created through the data importer. And if I, whatever, just click on one, well, I'll see the properties for the movie. And all of this has been, appended to my graph in that sense. All right, now let's complete this with the acted in relationship as well. So I now have persons, I have movies, and I also have the acted in data with me in this data set. So what I need to do is establish a relationship between the person and the movie. Call this acted in line with what I already have in my graph. And now I need to also choose the acted in data here. And this is a small data set. It just has the person ID, the movie ID, and the role that the person has played. So I'm going to quickly select the person, the file, first of all, which is the acted in file. And then I select the person ID, I select the movie ID, and I select the role. And now I already have a roles property, if you remember, on my acted in relationship. So I am going to change the name of the property here because I don't want two properties to be created. Oops. Yeah. Now there's one more thing I'll have to do here. If you see that I've selected different IDs for the person in the movie, that's because this is what I have in my data set. So I'll have to go back to my person node here and make sure that I select the same ID, because otherwise what will happen is it won't find a match because it will be doing the match on the name property, and the match would fail and essentially nothing would end up getting created. So I'll have to go back here and just make sure that I'm picking the same property here, and also for the movie, which is the movie ID. And I guess then I'm good to go. And then I can run the import. Right, so I see no people have been created because they were already created before. No movies either have been created because they've been created before. But I see that additional relationships have got appended to my existing graph, 372 in all. Now, if I go back to my graph, which I should have done earlier, but nevertheless, I think we still remember how many movies Tom Hanks acted in. And we're going to see if whether it brought back anything new in my data set. So I'm just gonna say active in, and don't worry about whatever that is. And I'm just gonna return the paths. That will be simpler. Read all this. Okay, and well, I get back 13 movies now. If you remember, they were initially 12. So there should be one movie which has got added, and I think it's Toy Story, which wasn't there in my earlier graph, which is got added. Right, so this is how you can append data to what you already have in your graph, and you can do this almost effortlessly, right? We didn't have to write a single line of code here. I already had some data in my graph, and as long as I had some data lying in a spreadsheet, well, all I had to do was just map it, and I could get back data, additionally written to what I already had. So essentially, data importer is an additive tool, and you can use it to bring data incrementally and add it to what you already have in your graph. All right, so that was data importer, and I'm just going to do a quick demo of Bloom as well, so that you understand the whole pack then, and then of course you can get into each of these in greater detail as you further your journey with Neo4j and AuraDB free. So let's go back to my instance. And the last option here that I'll be taking you through is Neo4j Bloom. Neo4j Bloom is Neo4j's de facto data visualization and exploration tool. It's again a tool where you don't have to write a single line of Cypher. Well, you can visualize your data graphically using this tool. It's also a great tool for business users because they're not savvy with Cypher. So the way it can work is IT can set up this tool for business users and make it available for business users to use. So let's look at Bloom. Once again, I'll have to log in here using Neo4j and my password. And once I do that, I'll be presented with this interface. And you can already see, okay, that came up pretty fast. So what happens is when this interface loads for the first time, we are presented with a perspective, something called as a perspective. So perspective is nothing but the schema behind your graph data, right? So whatever is in your graph, well, it will throw up the entities in terms of the labels and relationship types and properties in a perspective. Now the idea behind having something called as perspectives is, if you want to say if your graph has a lot of entities, right, hundreds of entities and hundreds of relationship types, and you don't really want to expose everything to the end user, so you can actually carve out a portion of what you want to expose, and you can create your own custom perspectives and make those perspectives available to the end user, right? So basically you're trying to carve out a subgraph from your graph and expose only that amount of information to the business user. So if I click on my person node, well, I only see two properties. That must be because I launched this before. So what I'm going to do is I'm going to just refresh my perspective so that I get back, and I get back the additional properties that I just loaded in my schema definitions. The same for movies. I get back all the movies, the additional properties that I've enriched my graph with. The same you can see with relationships. It brings back all the relationships that are there in my graph. And we look at saved Cypher in a bit. So what can I do in Bloom? Well, I can start by simply placing my cursor in the search bar. Right? I don't have to do anything else. And if you look at what it has thrown up, well, it has already thrown up a list of patterns that I can start to query on. So I don't have to really, use my thinking power, the ability of my thinking to understand what am I supposed to type here. I just place my cursor and I get a series of recommendations that are being thrown out to me. So let me start with movie. If I just select movie, well, what happens is I get back a bunch of movie notes, okay? And just like the browser returns you a bunch of notes, this is how Bloom returns you the node. And I can, click on any node. I can look at the properties of the node. I can look at the neighbors of this node. So what is the node connected to, right? And I can also look at the relationships. And there are some fun things that I can do in terms of styling here. So just let's cover that part and then move on. So what I can do is I can style my, the look and feel of my data in Bloom. So I can set icon for my label. So I can select maybe one of them. Okay, it's a little slow. Okay, yeah, so it's already come. So that's the icon assigned to my movie label. And then I can do things like, I can do rule-based styling. So I can, play around with the color and the size of my notes based on, some rules. So what I can do is, I believe I have a rating, IMDb rating from the new data that I've loaded in my graph. So what I can do is I can choose the rating, say for example, and I can color my nodes based on the rating. And what it has done is it has already understood what the min and max values for the rating is, and it has basically brought back those values to me so that I can set my midpoint and my color, and then I'm good to go. So let me choose something. Oops, it's too dark. Okay. Yeah. And let me set a midpoint for this. And what I can do is I'll say apply color. And immediately I see that my movie nodes are colored differently based on the IMDb rating assigned to it. I can also size my nodes differently based on the same, based on the same principle. So here it has already brought back to me the min point and the max point, and already also a size associated with it. I can make this bigger or smaller or whatever. And then I say apply size, and well, this is how it looks, right? So I can see that the ones which are deeply and darkly colored are the ones with a higher rating. So say if I click on this one, I see a rating of 8.1. At the same time, if I click on something much lighter, I see a rating of 5.6. Right, so this is how you can style your notes to stand out based on whatever it is that you're trying to depict in your graph. All right, and let me quickly just, assign something for a person. Okay, and now I can start to draw out patterns here. So say, for example, if I want to find people who have been associated with more than one movie, well, then what I can do is I can say movie acted in, I can say person acted in, and then I can say movie. And what I'm going to do is I'm going to clear my scene here and then run this. So this is what it brings back. Well, it is bringing me back actors who have acted in more than one movie. So that's what it's bringing me. That's what it's bringing back to me as form of the results. Right. So you can form patterns like this in Bloom. It's really simple, and I think there's no end to what you can achieve in terms of natural language search, because uh, you don't need to really understand how the entities are connected in your graph. You can come to Bloom and let Bloom recommend to you the search phrases that you can search on, and this way you can end up exploring the graph so very quickly, right? Even without having to write a single line of Cypher. So that was Bloom, and there is another feature which I don't think I quite have the time for it, but I'm just going to take you through this. We have something called a saved cipher. So these are search phrases that you can write upfront. Say, for example, if you have a complex cipher that you can't really represent using the search bar, well, then you can write your custom cipher to represent whatever it is that you're trying to search on, and you can save the search phrase. So if I just quickly show you. So this is the example, basically of a search phrase which was already configured for us in Bloom. So if I click on this, well, you can define a search phrase, a custom search phrase, and you can associate a Cypher query with the search phrase. So what this does is this becomes very handy for business users, because if business users have a specific question that they want to get answers to, well, then IT can set up these search phrases for business users, and they can simply come to this interface, and if you see, this is the search phrase that it shows up. Show me a graph, right? So similarly, if I have other search phrases set up, well, you can come to Bloom and search for it. Right, so that was Bloom. And if you need more information about Bloom, please visit the Bloom documentation, and you can learn more about it. Well, I am now quickly going to go back to my slides and just cover the last bit of what I had to cover. Maybe really, really fast, because I know I'm out of time. Right, so I'm just going to talk very quickly about the Graph Data Platform. Now, like I mentioned earlier, the Graph Data Platform is basically, everything that encompasses Neo4j at the heart of the ecosystem, right? So the heart of the ecosystem, we still have Neo4j, which is the graph database. But over the years, we've built a whole lot of tooling as part of this ecosystem to help you integrate your applications with Neo4j. And I'm going to quickly walk you through what these integration options are, so that these are available for you to use depending upon what it is that you're trying to build. So we have tools for all the personas. So we have tools, specifically for developers, for business users, for data scientists. We also have tools for administrators. Now, if you're trying to build an application in any of these popular languages, well, we have drivers available for you supporting each of these languages. So these are our official drivers that you can put to use to build any applications that you're writing to talk to Neo4j. And we also have a bunch of community drivers. So if you find something that's missing in this official list, well, you can also take a look at our community drivers, like say, for example, PHP or R or Perl or any of these options to talk to Neo4j. We also have a bunch of connectors that we've built with time. So say, for example, if you have something running on Spark, you want to bring the data from Spark into Neo4j or take the data out of Neo4j into Spark and do some processing, well, we have a Spark connector for you. We also have integration with Kafka. So if you have data lying in Kafka and if you want to bring data in or take data out to Kafka, whatever it is, we have both sync and source options available for you. We also have a JDBC driver, which can help you talk to any RDBMS. So if you have data sitting in an RDBMS, well, you can use our JDBC driver to bring that data to Neo4j. We also have a BI connector. So if you're working with BI tools like Tableau or Power BI or Looker or any of such tools, well, you can use the BI connector also to connect to Neo4j and use the tool to build your visualization. And very recently, we've launched a data warehouse connector. So if you have integration with, if you need to integrate your solutions with, say, Snowflake or BigQuery, or even Azure Synapse for that matter, well, then you can use our data warehouse connector to talk to any of these platforms. And then, of course, we have a whole list of APIs. We have a GraphQL API. If you're building an API using GraphQL, well, you can use a library to talk to Neo4j. If you have a Spring Boot application, well, you can use a Spring Data Neo4j framework to also talk to Neo4j. In terms of library, we have a few extensions that you can use. Though Cypher is powerful, but Cypher may not have everything that you want to do with it. So we have a utility called APOC, which is basically a kitchen sink utility. It is an extension of Cypher. So if there's something that you're planning to do with Cypher that you can't really find a way to do with Cypher, then you can take a look at our APOC library. And APOC, by the way, means awesome procedures on Cypher. You can take a look at this library, and I'm sure you'll find something that you can put to use. We also have a library that can integrate with RDFs. So RDFs are basically resource descriptive frameworks, another way to implement a graph database. And if you have an RDF graph sitting somewhere in your landscape, and if you want to integrate Neo4j with it, well, you can use the Neosemantics plugin from us. We also have a plugin for Kafka integration, but this is the predecessor of Kafka connector that came out much later. But if you wish to use this, I think this is also available for use. And finally, we have the Graph Data Science Library for all you data scientists out there who are wanting to do graph analytics on top of Neo4j. This library comes with over 65 plus algorithms. So please take a look if this is something of interest to you. Visualization, I just took you through Bloom. It was just a breeze, but of course, there's much more to Bloom than what I showed you. So do take a look at our documentation site if you want to learn more. NeoDash is also a dashboarding tool from Neo4j, which works really well with Neo4j. So do check this out as well if this interests you. DevTools, I just took you through the browser and the data importer. Arrows is something that we use to model the graph. Basically, like I said, we do instance modeling in Neo4j. So if you need an interface to draw, well, you can use the Arrows tool for it. And desktop is simply a thick client where you can install Neo4j locally on your machine and spin up databases. Yes, so that was a quick breeze through the ecosystem. And finally, I want to leave you with resources as to how you can continue your journey with Neo4j. Well, there are a wide variety of options here. Well, please do join our Graph Academy. It's a great place for courses, for resources. You can get plenty content to advance your learning with Neo4j. You also have dedicated learning paths, for different personas. So say, for example, if you're a data scientist, you might want to follow a particular path. If you're an full stack developer, you might want to follow, a particular path. So all of this information is available on our Graph Academy site. So do visit the site. And once you have taken our courses, you might want to validate your understanding by also getting certified. So you can take the certification that we offer. By the way, it's free, and become a Neo4j certified practitioner or professional, and show off, right? And of course, a whole wide variety of resources out there that you can take, that you can leverage in your learning, and basically your advancement of Neo4j. Right, so that's all I had for today's session and workshop. Hoping this was useful, and I don't really know what questions came along. I'm hoping that they've all been answered. Alex?
Yeah, that was super great. Thank you very much, Priya. What a great workshop today. I think that was really, really good, covering all the steps. We had a great experience, I think, in chat as well. Thank you again to Elaine, Shiny, and to David for helping out with all these questions. I think we got through with small hiccups when people were struggling a little bit with the movies data set to be created, but we did a recap, and I think everything went well. The slides will be available, so we will share these with you, so you can all check out the links, especially now at the end, but also more at the beginning when there was some other content on there. The code examples that Priya has used today will also be shared in the GitHub repository, so you can check out later again and do some other trial with the code and with the queries, and play a little bit more. I shared the links for next steps, basically the Graph Academy and the upcoming training. So I think that's great. Plus all the other stuff you already mentioned. So I don't even have to say what I wanted to say. I think it's all you covered it already. So again, thank you very much for presenting this today. Thank you all for attending. I mean, it was really fun. I heard a ping from David earlier. This is actually so much fun to take part in this, because you all been so interactive and so lively, and lots of questions, lots of interactivity. So that's more fun for all of us if you are enjoying this as well. So I think we did this. This is basically mission achieved, I would say. Tomorrow we do another workshop, so Road to Notes continues. Tomorrow's session will be on healthcare analysis. So if you haven't registered, please do so. Same time, almost same place, but you need to register for it, otherwise you don't get the login link. And I think with that we are at the end. I hope you enjoyed this. Again, if you have continue working with Neo4j, like to explore more, are struggling with something, join our community or our Discord server. Lots of people there to help you out with questions and answers. And with that, I wish you all a great rest of your week, rest of your day. Thank you, Priya, and take care, everybody.
Yeah, thank you, everyone, for joining in, and have a great rest of the day. Thank you.
Bye.
Bye-bye.